I want you to take a piece of paper and fold it in half. This simple act can help us grasp a complex concept in physics. Now imagine a tiny ant wanting to travel from one side of the fold to the other. The ant represents us trying to navigate the vast distances of space. It could crawl across the paper, taking the long route, or it could take a shortcut, a hole punched through the fold. This shortcut is what we call a wormhole. That hole, my friends, is like a wormhole. It's a theoretical passage through space and time. In the vast expanse of space-time, wormholes are theoretical tunnels that bridge two distant points, making travel across the universe much faster. Instead of traveling the long way around, a spaceship, or perhaps even a beam of light, could enter a wormhole and emerge on the other side of the universe, light years away, in a fraction of the time. These cosmic shortcuts are predicted by Einstein's theory of general relativity, which tells us that gravity warps the fabric of space-time, creating the potential for these fascinating tunnels. While we haven't observed wormholes directly, their existence remains a tantalizing possibility that excites both scientists and science fiction enthusiasts alike. Think of it this way. If the universe is a giant sheet, a wormhole is like a wrinkle that connects two distant points on that sheet, offering a shortcut through the cosmos. This wrinkle could revolutionize our understanding of space travel. There's a catch, however. Wormholes are notoriously unstable and can collapse at any moment. To keep a wormhole from collapsing in on itself, we'd need something quite extraordinary, exotic matter, which is not easy to come by. Exotic matter, as its name suggests, is a hypothetical type of matter with bizarre properties, such as negative mass, which defies our usual understanding of physics. Imagine a ball that falls up instead of down. It's a mind-bending concept. That's the kind of weirdness we're talking about. It's not something you encounter in everyday life. This negative mass would create anti-gravity, pushing the walls of the wormhole outward and preventing it from collapsing, making travel possible. While we've never observed exotic matter in the universe, its existence is not ruled out by the laws of physics as we understand them. Think of a bubble. Without air pressure inside, it would collapse. The same principle applies to wormholes. Exotic matter would act like the air pressure, keeping the wormhole inflated and passable, allowing for potential interstellar travel. While exotic matter might sound like pure science fiction, there is a real phenomenon that hints at the possibility of negative energy. The Casimir effect. This intriguing effect is named after the Dutch physicist Hendrik Casimir, who first predicted it in 1948. In this experiment, two uncharged, perfectly flat metal plates are placed very close together in a vacuum. The distance between these plates is typically just a few nanometers, which is incredibly small. Quantum fluctuations in the vacuum energy create a small attractive force between the plates, effectively pulling them together. These fluctuations are a result of the ever-present, ever-changing quantum fields that exist even in empty space. This tiny force can be explained by the presence of slightly less energy between the plates than in the surrounding vacuum. Essentially, the energy density between the plates is lower than the energy density outside them. While not exactly the same as negative mass, the Casimir effect demonstrates that negative energy densities are possible, lending a sliver of credibility to the idea of exotic matter. This opens up fascinating possibilities in the realm of theoretical physics. Think of it like this. The Casimir effect is like finding a small area of slightly lower pressure in the atmosphere. Just as atmospheric pressure can vary, so too can energy densities in a vacuum. It's not a vacuum, but it shows that variations in energy density are possible. These variations, though minute, could have significant implications for our understanding of the universe and the potential for harnessing exotic forms of energy. Imagine a wormhole as a tunnel. It would have two openings, called mouths, connected by a passageway called the throat. A spaceship would enter one mouth, travel through the throat, and emerge from the other mouth, potentially billions of light years away from where it started. The size and shape of a wormhole could vary. Some might be spherical, while others could be more elongated. The stability of the wormhole would depend on the distribution of exotic matter within its throat, ensuring that it remains open and traversable. Think of a drinking straw. The openings are the mouths, and the straw itself is the throat. The stronger the straw, the more liquid or spaceships it can handle. Section 5. Black holes and wormholes. A mysterious connection. Black holes, those cosmic monsters that devour everything that crosses their event horizon, might be connected to wormholes. Some theories suggest that the singularity at the heart of a black hole could be a gateway to another universe, with a white hole acting as an exit point. A white hole is the hypothetical opposite of a black hole, spewing out matter and energy instead of consuming it. While we've never observed a white hole, the mathematics of Einstein's equations allows for their existence. Imagine a black hole as a giant cosmic drain and a white hole as a cosmic fountain. A wormhole could connect the drain to the fountain, creating a cosmic shortcut through space-time. Section 6. Quantum wormholes. Tiny tunnels in space-time. On a much smaller scale, the realm of quantum mechanics suggests the existence of quantum wormholes. These subatomic tunnels would be incredibly small, fluctuating in and out of existence on a timescale so short that they would be impossible to observe directly. While these tiny wormholes wouldn't be useful for interstellar travel, they could have profound implications for our understanding of the universe, potentially connecting different points in space-time and offering new insights into the nature of quantum gravity. Think of the foam on top of a cappuccino. Each bubble is like a tiny, fleeting quantum wormhole, constantly forming and disappearing within the fabric of space-time. Section 7. The instability of wormholes. A cosmic balancing act. The biggest challenge with wormholes is their instability. Even the slightest disturbance, such as a spaceship trying to pass through, could cause a wormhole to collapse faster than the speed of light. Maintaining a stable wormhole would require an enormous amount of exotic matter, precisely distributed to counteract the immense gravitational forces at play. Even then, the stability of a wormhole would be a delicate balancing act, vulnerable to the slightest perturbation. Think of a soap bubble. It's beautiful and delicate, but even the slightest breeze can cause it to pop. Wormholes are even more fragile, requiring a cosmic balancing act to keep them open. Section 8. The future of wormhole research. Unraveling the mysteries. While wormholes remain firmly in the realm of theoretical physics, scientists continue to explore their properties and implications. Advanced computer simulations and new theoretical frameworks might one day shed light on the feasibility of stable wormholes. Perhaps future generations will unlock the secrets of exotic matter or discover new physics that make wormhole travel a reality. Until then, wormholes will continue to captivate our imaginations, reminding us of the vast mysteries that still lie hidden within the fabric of the cosmos. Think of the early days of flight. People dreamed of soaring through the air long before airplanes became a reality. Perhaps one day, wormhole travel will make the jump from science fiction to scientific reality. Section 9. Conclusion. Wormholes, bridges to the unknown. Wormholes Those tantalizing shortcuts through spacetime remain one of the most intriguing and perplexing predictions of modern physics. While their existence is far from certain, the possibility of traversing the cosmos through these cosmic tunnels continues to inspire scientists and dreamers alike. As we continue to explore the universe and unravel the mysteries of gravity and quantum mechanics, we might one day discover whether wormholes are merely figments of our imagination or bridges to the unknown, waiting to be crossed by intrepid explorers of the future. Until then, let us marvel at the wonders of the cosmos and the infinite possibilities that lie hidden within its vast expanse.